Okay, thank you all for being here and giving me the opportunity to present my work. So today I will mainly discuss about the ultra thin visco film that is showing superconductivity around 90 Kelvin. But this film is quite inhomogeneous, that's why it gives a broad superconductivity transition. So today I will mainly talk about this from the quantitative modeling, also how we can understand this broad transition of this superconducting film. Okay, I will start from the basic aspect of superconductivity. So in this case, superconductivity can be explained by a macroscopic wave function. So that has mainly one part is the amplitude and one is the phase coherence. So in amplitude, there are mainly people have seen of the such kind of inhomogeneous film. So there is a local variation of this superconducting gap, and that leads to also variation in local transition temperature. So this mainly arises mainly of the disorder, also in the doping inhomogeneity and other things. And other things is the phase coherence picture or phase fluctuation picture. So they are mainly in this formalism they have mainly assumed that your amplitude is constant all over the place or uniform. They are mainly talking about the phase pictures. So there are quite known model is already there. That is one of the BKT transition, also thermally activated phase slip model. So that is the Ambe-Gaoker-Halperin model. Also some vortex crossing, vortex dynamics, but all they are leads to the phase fluctuation and phase coherence. So first I will talk about this amplitude disorder picture. So here mainly it comes from in visco there are many independent parameters which can affect this TC, mainly for this thin film local strain, also these defects, interface effects, also oxygen stoichiometry, and all these are effects actually independent almost quite. Also they are giving contribute additively to C. So from the central limit theorem I can then assume that the film has local TC distribution and which can be explained in terms of normal or Gaussian distribution. So this is my simple normal Gaussian distribution, and this is the mean temperature TC naught, and this is the standard deviation of this distribution. And at a particular temperature the major resistance, macroscopic resistance, so that can be the only comes from the region which is normal at that temperature, and the region which is superconducting they are not giving the contribute to the resistance. So from here we have calculated the resistance analytically. Also there is another term called superconducting fraction. So this actually indicates how much fraction of the film become superconducting progressively with temperature or reducing the temperature. So these two are the analytical formula, but it will help me to quantitatively analyzes my resistance versus temperature curve, also other things that I will discuss effectively. And also at very high temperature above your TC mean, so RT is almost normal state resistance, also the superconducting fraction is 0, and close to and below TC mean, so superconducting progressively increases and superconducting fraction become 1 at very low temperature. So this is the one of the simulated curve using that previous formula that I have derived. So it is the resistance transition of the superconducting. So we have seen that from this inhomogeneous strain or standard deviation. So for small value it is a step-like transition to a higher inhomogeneity strain. The RT curve actually form a smooth crossover. And also this is the corresponding Gaussian distribution of local TC of the film. So that is also broadened at for this higher standard deviation or inhomogeneity strain increasing when it is. Also this is the superconducting fraction. So it explains how gradually the films become superconducting. Okay, this is the other two analytical parameter that I calculated from this Gaussian distribution. So one can experimentally people are defining that transition width. So that is the separation between these two, T90 minus T10. So T90 is the actually resistance at which the resistance falls, or temperature at which the resistance falls 90% of the normal state resistance, and 10%, and T10 is the 10% of the normal state resistance. And these two definition actually leads to the transition with delta T, that is well known in the superconducting community of this, how they analyze their broad transition temperature. Also if you take the derivative of this curve RT, that is dr dt, that also FWHM give you the kind of the transition temperature width. So this is the two formula which will can independently capture the means this broadening or the inhomogeneity strength of the sample. So this is the experimental RT curve resistance of temperature, and there you can see that the Gaussian model can means fit almost very well. And from this previous formula I have calculated delta T around comes around 11.8 Kelvin, so that is the transition width. So from this kind of inhomogeneous film, and this is the corresponding Gaussian distribution that I have extracted from this fitting parameters, and this is the corresponding superconducting fraction, so that will successfully use in the later analysis. And this is the, and that means if you take the dr dt, from here also calculate FWHM, and from here also calculated sigma comes around 4.1 Kelvin, or in this model it is comes around 4.62, so that are quite close, not exactly same, but it is quite close. So it is also a cross check that Gaussian model can exactly capture the this broad transition of this film. Also the other picture is the phase fluctuation picture. So in this case, this is a type 2 superconductor, so vortex is already there and it's a defective film. So vortex is almost p near different disorder positions. So when we applying the current in the sample longitudinal direction, so vortex will cross the perpendicular to the current flow, means across the width of the sample. They feel this Magnus force or similar to Lorentz force. So this vortex moves from one width of the sample from left to right. So that time there is a change of phase 2 pi. So that is a 2 pi phase change actually called the phase slip in this kind of means phase picture. So yeah, and when there is a change in phase according to the Josephson relation, you can get a voltage, that is the change of d phi dt multiplied by h squared by 2e. And if you have vortex crossing rate it so tau, that time you can get or gamma, or you can get this phi naught by flux quantum into tau. And thermal vortex is usually pin in the defect. So when vortex have to cross from the one side of the other side, so they have to overcome this thermal barrier. So that is mainly the U. And in Josephson system barrier that I comes later. So usually that is, this barrier should be comparable to the 2EJ. EJ is the Josephson coupling energy. So in this inhomogeneous film, so there is a Josephson network, and the transport is happen through that inhomogeneous network. That's why this Josephson coupling energy comes in the picture. Yeah, and this is the Josephson Wasser potential, and that is showing that yeah. So this is a change of phase 2 pi corresponding a vortex have to cross it 1 minima to other minima, they have to cross this energy barrier almost 2 EJ. Okay. Yeah, so this is the one of the model called Ambe-Gaukar-Halperin model. So that actually captured this phase fluctuation or phase incoherence in kind of means thin disorder film. So here you can see that this is the this is the exact form of this Ambe-Gaukar-Halperin model. So here the dimensionless parameter EJ by cavity that actually control the overall transition, and this is the ICT, and ICT is almost linearly with T. Yeah, this is the also same RT data but fitted by this phase fluctuation picture, and that gives you TC according to 92 Kelvin, but this is the only TC on set, so that is almost close to the BISCO 2212 phase, and this is also the RNS plot. That is also give you delta U some number, but I will show you that this at 90K this ratio is quite, EJ versus cavity is quite less, but exactly at around 85.6 Kelvin this EJ by cavity actually comes to close to 1. So this is remarkable. So this temperature is very close to the Gaussian mean temperature that I have already extracted from the Gaussian model. So these two models are, though they are different aspect of superconductivity, but they are quite close, means connected closely. Also this delta U comes around 2.3 EJ that I previously explained, 2 into EJ. So that is also saying that is phase slip is thermally activated. So that is also one of the proof thermally activated phase slips. Also after that we have done some two coil mutual inductance susceptibility measurement, and here we have also modeled this susceptibility by a choice domain susceptibility means analysis. So that is for the effective medium theory. So susceptibility depends on the superconducting fraction, and it is a shielding factor Z lambda, and that is depend on the dimensionless parameter ratio of means physical characterization length of a superconducting region and the temperature dependent means penetration depth. But in this picture you can see that this susceptibility onset comes around 70 Kelvin. But if you see my RT curve, that is comes around 90 Kelvin. So there is a difference almost 20 Kelvin. So to incorporate the delay response, I have modified this equation by CST into C effectivity. So that is multiplied by superconductivity function into a connectivity vector. That is the form of this analytical form. And this is explain how this superconductivity phase coherence is developed with this. And after that we have done some background calculation to only extract the superconducting contribution. And this is the superconducting contribution.
You are going in negative time, huh?
Yeah, just done. Okay, so this is the fitting of this susceptibility data, and it is well fitted by this model. And this, if you assuming lambda equal to suppose 400 nanometer in this kind of polycrystalline film, so that gives you the superconducting region means patches side around 13 nanometer, but it is mainly the magnetic characterization length or screening length you can say. But at low temperature this model deviated, it is comes around T cube, but we don't know the exact region of visco why it is T cube at this low temperature. And this is the overall phase diagram, means showing kind of evolution of superconductivity from this 92 Kelvin to around 65 Kelvin. There are different stages of pairing mechanism and phase coherence. Yeah, and this is the kind of summary what we analysis. Okay, thank you.
Okay, thank you, sir. Any questions from audience? One very sharp question if you have. If not, I'll ask one question. This TC that you are talking almost all the slides. So it depends, you wrote in oxygen vacancies.
Yeah.
How does it depend?
Means if your oxygen doping is less,
Yes.
then actually TC is shifted to the lower temperature. And in the optimum doping, you can come some sharp transition or maybe around 90 Kelvin, that is visco intrinsic one for the bulk case. Good optimum doping.
So why? What is the reason? Of course, maybe oxygen may be excess, maybe deficient.
Yeah.
So how does it change the TC?
I mean in this
TC,
kind
what
of
is TC? Actually defined it first.
this is the transition temperature where resistance actually start dipping from the normal state resistance.
Yes.
So that is the transition.
Oxygen what playing role to change the TC? Or in terms of resistance, let's say.
Yeah, actually in this kind of film, the Cooper pair moves in the CO2 plane, and I think oxygen deficiency leads to somehow means there are some normal region locally forms, maybe if there are oxygen deficiency at that region. So that region may be locally non-superconducting or kind of defective regimes. That's why, or maybe there are some oxide regime.
Or is it something with to do with the bond length, bond angles between the samples element? The oxygen is bonding with others.
But I don't have that much structural.
Okay. So next speaker, let's thank Santanu again.
Yep.
It's a wonderful talk.
So, hi, I'm Harshit from IMSC Chennai, and I'm going to talk about thermal fluctuations of emergent gauge fields in cuprates, and how do we see different orders, and how do we see whole pockets with fractionalized area, and what is the mechanism of high TC superconductivity in cuprates. So let's get right into it. So this was the phase diagram. I think most of you might have seen in Subir's talk, and this is the phase that we are interested in, and this is the transition that we are interested in. And we will start at the place where Subir ended. So he called this phase the FL star phase, and this phase the conventional FL phase. So we will study this FL star phase and how the transition from superconductivity happens, and how do we reach this FL star state, and what are the properties of this FL star state. What is the idea behind this theory? So the idea is that you have the single band Hubbard model, and then you can write it in terms of nearly free electrons which are coupled to so-called paramagnons. This is the picture. So you have these C alpha electrons which are coupled with some decoupling field lambda to these paramagnons, which are essentially quantum rotors. And this has been the starting point for many theories which have tried to explain different aspects of cuprate phase diagram. One of the prominent ones is what is called the spin density wave theories, or spin density wave order. Now the new idea here is we don't fractionalize the electron, we fractionalize these paramagnons and then create new degrees of freedom, which can explain some distinctive features of this pseudograph phase. So how does this fractionalization happens? So what we do is we fractionalize this paramagnon, the spin 1 part, so we take the lowest 2 spins of this quantum rotors, so s equal to 0 and 1, and we fractionalize that to have these 2 spins s1 and s2, which are spin halves. And the spin, so s1 is coupled to the upper layer with this Kondo coupling jk, and s1 and s2 are coupled among themselves with this jperp. Now how do you see both the phases FL star and FL in this theory? So if you have this jperp is much larger than this Kondo coupling, then what you will have is these ancilla spins will form a trivial insulator, and you will have a large Fermi surface only of these electrons, which is the FL phase. But if you have Kondo coupling which is greater than jperp or much larger than jperp, then these two will hybridize and you will get the small Fermi surface, or the whole pockets that we get in cuprates in the pseudograph phase. And what these spins do, the bottom spins, they form a spin liquid, a special kind of spin liquid in this theory. Now, what are the key ingredients of this ancilla layer model that we call so? So you have the electrons C alpha, which are coupled to spin S1s through this coupling field phi, and then these two are coupled with this field B. Now how do you attain the different phases depending on these two fields? So this field phi, when this is 0, then these two layers will decouple from the upper one, and you will get only the large Fermi surface and the FL phase. But in FL star, this average phi is non-zero, so it is coupling to the second layer, and then the coupling to this second layer gives you the FL star phase and the area p by 8 whole pockets. And what this B field does is this couples the lower spins to the upper two layers, and what we do is we take this B field and this U field corresponding to the spin liquid, and we study the thermal fluctuations of this B and U fields, and then couple it to the upper layer to get electronic spectral functions and other properties. So first I will start with a theory where you study only B and U and their thermal fluctuations. So what we can do is we can write an energy functional for B and U by including all possible terms in a Landau-Ginzburg expansion, and that all the terms that are allowed by symmetry properties of B, and also gauge invariance, because SU2 is the new gauge field, but finally we don't want anything to depend on this gauge field, so we want everything to be gauge invariant at the end of the procedure. Now we can write the energy functional in terms of epsilon2, which is the quadratic terms. So you have the B dagger B term, and you have the hopping term B dagger U B. You have the magnetic term for the gauge fields U, and then in the phase where B condenses, to stabilize you need quadratic terms as well. So you have this fourth order term. This rho I is what is called, so I will explain this first. So you have these order parameters in this theory. So first important order parameter is the site charge density, which is just gives you the value of charge at a site I, which is B dagger B, which is called rho I. The other two, bond density and bond current, are not that important, but the last one that is most important for superconductivity is the pairing amplitude, and this is given by this B correlation with gauge field U in between to make it gauge invariant. And you can write the quadratic term in form of all these order parameters. So rho I square essentially means B to the power 4, because rho I is B dagger B, and then all terms that are possible in this theory you can write them like this. Now what happens when you take these two terms, epsilon 2 and epsilon 4, and minimize the total energy at 0 temperature? So you minimize the total energy functional within a mean field ansatz, so you take Uij to be identity. So this is the first approximation, at the first level of approximation, and we see you get different phases. So this is the D wave superconducting phase, the famous dome in the cuprate phase diagram, and you get other phases which are charge density wave phases, where the charge density modulates with some period in the x and y direction, which is 4 times 1 means period 4 in the x direction, period 1 in the y direction. And what we do, we start at 0 temperature, we start with this phase DSC, and then we want to see what happens when you include gauge fluctuations and thermal fluctuations of gauge and charge, the scalar field charge on field B. So how do you do this? So you write, so you know the most general energy function, partition function for this energy function epsilon 2 plus epsilon 4 could be written like this. So what we can do is we can minimize this. We can do metropolis accepted criteria for this total energy functional by sampling B and U, and then there is some details of how you sample them, but that is not important. So we can sample B and U at different temperatures T according to this weight exponential minus E by T, and then we can get different values of configurations for B and U at some finite temperature T. Now what happens at extremely low temperatures? This is the bond density plot, and you see that there are these very interesting looking areas where you get vortices and anti-vortices, and how do you identify them? You plot the angle of the superconducting order parameter, and we see that as you go around a pinch point, this vortex or the anti-vortex, the phase changes from minus pi to 2 pi because the color changes from this red to the other edge of the red. So one of the pair is vortex and the other one is anti-vortex. So at very low temperatures you get a dilute C of these vortex and anti-vortex. And one interesting observation is if you zoom into one of the vortex, I zoomed into this one, you get this striped order, and this was seen long time back, almost 2 decades back, by Hoffman and his group at UC Davis, where you see this these stripes which are quite similar to these stripes. These are vortex scores that they mapped in STM experiments, and you see these stripes. So this is an important observation in our calculation. Now the other one is, if you see this argument at different temperatures, you see that low temperatures it is almost phase coherence, and at high temperature there is no phase coherence. So there is a transition happening here, and we quantify that transition by using something called the superfluid stiffness, where you calculate the change in the free energy of the system when you include a twist at the boundary of the system. And we see that at high temperatures you have almost zero superfluid stiffness, which means no phase coherence, and at low temperature you have some finite phase value of superfluid stiffness, which means a high phase coherence. And you see a transition here. This dashed line gives you the value of the transition temperature here. The other important, so this is the last one, the other important property is the so-called Fermi arcs. So for a Fermi liquid you can get this full Fermi surface, but for pseudo gap you get these arcs which are not, which do not merge with the edge. So basically you don't get the full Fermi surface. And we see that if you include the thermal fluctuations of B and U, we also get these Fermi arcs in this calculation. And low temperature we get the whole pockets with the appropriate area. So this is the study of this pseudo gap phase and its transition to DOF superconductivity. And what we claim is that pseudo gap is a fractionalized Fermi liquid, the FL star, with whole pockets and a background quantum spin liquid. And this transition from DSC to FL star is a KT transition, where you have proliferation of vortex and anti-vortex, and each vortex contains this stripe pattern which we see in experiments as well. And we also see Fermi arcs when we can include thermal fluctuations of B and U, and other effects that were seen were quantum oscillation effects as well, and Yamaji effect, which Subir also showed in his talk. What we would like to do next is to include fermionic spin-ons being dynamical and then see what effects those have, and this paper actually contains first study of that with Subir as one of the authors. So thank you.
Thank you. So questions? Any questions? No? So let me ask, this calculating the B and U, you are basically showing the transition, superconducting transition.
Yes.
Yeah, these are theoretical.
Yeah, these are theoretical calculation.
But experimentally, how one can do that?
Experimentally, okay, I'm not exactly sure how do you measure superfluid stiffness, but people claim that it is larger in the SC phase, but I'm not sure exactly directly how do they measure it, the stiffness. But I don't know. I don't think the twist mechanism is there. I think indirectly they should probably measure that. So if you see a phase coherence, you will expect the superfluid stiffness to be larger. So maybe there is some way where you can correlate that to the superfluid stiffness.
Okay. Yeah. Okay, Arshad, thank you. Thank you. Yeah. The next speaker.
Okay, hello, good afternoon everyone. I am Poulami Sarkar, and today I will present my work on evolution of vortex states and inhomogeneities in disordered 2D superconductors in the presence of orbital magnetic field. And first of all, I would like to thank my supervisor Amit Ghoshal and my collaborators Student1, Anushree and Anurag. So today I will address 5 central questions of our study, and then I will address each one by one. To start with the first one, how do the joint perturbation of spatial disorder and orbital magnetic field modify the inhomogeneous response in superconductors when they compared to when they act individually? So in clean system, we know that the local pairing amplitude and the coherence peak height are well correlated, and when we introduce weak disorder into our system, this correlation drops. But as we increase the disorder further, or we introduce the magnetic field into our system, this correlation drastically drop, and they also disrupt the spatial distribution of these parameters. So by this we can answer our first question, that not only the dual perturbation of disorder and in magnetic field disrupt the spatial distribution of both the parameters, but they also destroy their local correlation, by which we can say that in experiment when we try to represent the local pairing amplitude by the coherence peak height, this will not be that much trustworthy when there is strong disorder or magnetic field into our system. Secondly, we'll address how can local spectroscopy distinguish between the Abrikosov vortices and the Josephson-like excitations seen in highly disordered thin films. So first look into these two plots where in weak disorder cases the disorder disrupt the superconducting pairing amplitude scenario, and when high disorder it will suppress the disorder, the super pairing amplitude in some regions. So now when we introduce magnetic field into our system, the in weak disorder case it will create Abrikosov vortices, but while disorder is strong, it will the field line will try to penetrate to the region where the superconductivity is already destroyed, that is there is already no states available. So when we look into the spectral distribution, when we look into the energy spectra of that region, we see that there is a accumulation when there is weak disorder, which indicates that there is a Abrikosov vortice, and when there is and when the field line passes through an insulating region, we see there is no state accumulation, which will indicate that there is a coreless Josephson vortex which doesn't show any metallic property at the core. Now by uniquely describing these features of the two vortices, we can identify them in experimental cases. You can see these these right two panels are from experiment, where we can in this region where the vortex line where the vortex penetrates the system, there is an accumulation of state locally, which indicates there is a Abrikosov vortex which is being generated, and when there is already superconductivity suppressed, and if field line passes through this kind of region, we will get a suppression of local states at this region, which indicates that there is a Josephson kind of vortex. Now we will come to our third observation, that how do the microscopic rearrangement modify the transport, and how does the supercurrent navigate in the background of emergent electronic granularity. We can see that in clean cases the supercurrent flows through a circulating pathway around the vortex core. Now as we increase disorder, these circulating pathways are disrupted, and it tries to and the supercurrent are forced to pass through a percolate the arrows are not seen properly, but the supercurrent tries to passes through the narrow superconducting regions, forming a global loop to maintain the current to be zero. in our system. And as we increase this magnetic field and disorder both in our system, we eventually see that this supercurrent flow totally disrupted, and by this we can answer our question that with increasing field and disorder in our system, the ordered supercurrent shatters, and it will become a very percolative kind of pathway of supercurrents. Now we will move to our fourth question: what is the fate of zero energy calorie-dense matrix on coarse states in the presence of disorder? What is the fate of these CDGM peaks? So we know in clean case, at the vortex core we generally get a CDGM peak in our energy spectra, but when we introduce a weak disorder into our system, we get a pseudo gap, which is very distinct from the superconducting gap. So we will address how this pseudo gap generates. So first see, when we apply when we put a single impurity at vortex core, we can see that this impurity will try to scatter the bound energy states from zero energy to a positive or negative energy depending on the sign of the impurity, and this result exactly matches with the Bagwell calculation, with the deflection coefficient calculation from the Bagwell framework, that a negative impurity at vortex core will shift the CDGM peak to the negative energies, and as we have box disorder in our system, so we can say the disorder will generate a unique disorder environment locally. So the ensemble averaging of these all these vortex cores will give us a suppression of zero energy at local vortex state, so that we are getting this kind of pseudo gap in instead of the CDGM peak when we introduce disorder in our system. Now we will finally address how does the vortex evolve from conventional metallic Abrikosov cores to fully gapped Josephson vortex cores. So see, this is low disorder case where we see that we have a well defined gap when there is no magnetic field, and as we introduce magnetic field into our system and increase it, the gap starts filling up. But we see for high disorder case that this kind of gap is insensitive to magnetic field. So we will try to connect these two very extreme pictures. So first we will start seeing how this how the strong disorder case is governed by which kind of physics. So in case of strong disorder, we already said that the vortex lines, the field lines will try to penetrate through the regions where the superconducting pairing amplitude is already suppressed. So there is already no states available, and the vortex is residing in a Anderson localized regions. So the course the vortex core is already governed by a normal state physics, and thus the score spectrum is being independent of field. So these two extreme pictures, that the pseudo gap in low disorder and the hard gap in the strong disorder, is basically a spectroscopic migration of the vortex core states, and this plot will finally explain what actually happens here. So as we increase disorder in vortex core, the impurity will try to push the CDGM states from the CDGM states from zero bias to the bulk gap edge, and when the bound energy reaches the bulk gap, it will lose its confinement and it will merge with the continuum, and thus it will create a hard gap when there is a strong disorder in our system. Thus we bridges these two extreme pictures, and we explain how the how the disorder evolves the vortex state, and thus I conclude. And this is the theoretical framework by which I have done all my theoretical calculations and simulations. We have used self-consistent BDG solver, and we have used the 2D attractive Hubbard model in presence of non-magnetic impurities, and with this VI, and we have incorporated orbital magnetic field with Peierls phase factor, and we self-consistently solve our self-consistent fields, the local pairing amplitude and local density, and we have also calculated the current, local current from this framework, and again I will conclude my talk by acknowledging my collaborators and supervisor. Thank you.
Thank you, Paula. Is there any questions from audience?
Thank you for a very nice talk. I wanted to ask, the disorder is random, right? In this case?
Yes, random disorder.
So, does the crossover in your slides, would it depend mainly on the disorder strength, or also it could depend on the spatial correlations of the disorder?
Which one?
Your disorder, if I maybe change it to a correlated disorder, does it affect the crossover regimes or other things?
Though I haven't checked, but in our group they have we have actually tried with different kind of different distribution of disorder, and mainly Gaussian and box, all this, and we have found that the disorder will not change the distribution of disorder will not change the pattern of this crossover that much.
Yeah, what if there is a correlation? I mean, not random, rather a disorder at any site is also dependent on the disorder along outside of it or surrounding it.
No, actually it not. We have tried with different kind of disorder that we have the Gaussian disorder at any point. There is a strong disorder at the vortex core, and it normally decreases to around the vortex core, but it will not change the crossover pattern actually.
Okay, thank you so much.
Thank you, very nice talk. In your second slide, there is some experimental mapping, I think.
Yes.
So what kind of technique that one? Yeah, I think this one.
Oh, this one.
Yeah.
You want to know about the material?
No, I asked you the experimental technique.
STM.
STM.
Yes.
Okay, and what is the material?
This is SR2VO3 FEAS.
Okay, so it is already type 2.
It is a type 2 superconductor.
Thank you.
Yes.
Follow me, very nice talk. So I wanted to understand the difference between what because of vortex and perception vortex. Like how it is different.
So you can see when there is weak disorder in our system, when we turn on the magnetic field, the vortex line will pass through the system. Mainly, they will not. They will, of course, they will preferentially pin at the region where the vortex is high. But the disorder is high. But as in our system, the disorder is not that much high in our system. So they will try to maintain their intervortex distance so that the cost is minimum. So in this scenario, when the vortex passes through any region, it is already passing through a region where there is, if we consider the normal side, there are states available basically. So when the field line passes through that region, the magnetic field will try to break the Cooper pair and there will be normal electronic states which will form the Henry bound state in Henry bound states, and this this can be understood by the accumulation of electronic states, where there are if you can see that there are in the other superconducting regions where there is no field line penetration, there is a black thing which is which indicates the gap. But in this there is no in this point there is no gap, there is accumulation of states due to the formation of Henry bound states, which indicates that there is a abricosal vortex, mainly which has a metallic core.
And what is Josephson like?
Yeah. So now you see in this plot there is no magnetic field. The superconductivity is destroyed in this region by only disorder. Okay, so there is no states available in that region already, and now the vortex will try to pass through that region to minimize this cost. You can see previous papers from our group that we have shown that vortex will preferentially pin at that region when there is strong disorder. So in this scenario, when the vortex passes through that region, it can't form the Henry bound states as there is no states available. So when we look into the spectra, we do not see the accumulation of states, which is very much obvious in case of abricosal like vortices.
Okay, thank you.
Thus we distinguish these two from our theoretical framework.
Well, so these are the experimental data.
Yes.
Done by using
STM.
So highly ordered thin films and ordered thin films and disordered thin film. Can you distinguish using STM?
Yes, of course. In ordered thin films, we can see in STM that the superconducting gap will be homogeneous. The superconducting gap. But in disordered thin film,
those data, the color code showing here, the 0 to 8.
yes.
Right? What is that?
This is basically the gap, the value of the gap.
So you are measuring directly?
Yes, they are. We are collaborating with the experimental group, and they are measuring directly.
What the experimental data, the color it shows, right? So what those color means? Like 2 to 8, 0 to 8.
Oh, this 0 to 8 into 10 to the minus 2 eV. Sorry, I forgot to mention. Yes.
Energy.
Yes.
Okay. This is DIDB.
DIDB, conductance basically. Okay, thank you. Thank you, Paul.